Recording. Okay, the session should be recording. Audio is up. We are live. Welcome to Lecture 12, Instructional Analysis. Today we start having some real fun with shear and moment diagrams. Last time we just talked about internal shears and moments at a particular point, and now we're going to see if we can determine internal shears and moments everywhere. And so that's what a shear and moment diagram is. But what I want to do is I want to take our first real foray into shear and moment diagrams and tie it to what we did on Friday, because we're going to be able to use what we did Friday as a spot check to see whether or not what we're doing today makes sense. We can actually determine what we computed Friday using today's example. But, you know, that's running. Let's start with walking. You know, walk before you can run. Couple quick announcements. So the attendance grades are up to date. One thing I'll say about the attendance grades, there was a setting on Blackboard that I had set up. When you're doing Collaborate, you can set Collaborate up to automatically calculate your attendance data, but it was actually doing it kind of incorrectly. So I turned that off, and what that should have meant is pretty much for everybody in the class, if you've had perfect attendance, it didn't matter. But if you had missed a day or something, then your grade, for some reason, was turning out lower. So while I fixed that, just about everybody's attendance grade went up like a little bit. So I just wanted to clarify that for you. I fixed that error. On the homework assignments, so we're trucking along. So homework 3.4 has been graded. The solution is posted. So you got everything in regards to trusses. Homework 4.1 was due today, and now we're in homework 4.2 land, which is going to be our first drawing shear and moment diagrams. I'm going to pull up the chat here on this other computer. Okay, so let's get into shear and moment diagrams, and today we're going to explore the graphical approach, the way that we can just sort of look at a beam and just draw it. No calculus or anything like that. Now, to be clear, while we're not going to be doing any calculus or deriving any equations or anything of that nature, we do want to make sure that we understand the relationship between loads, shears, and moments. So the idea is basically if you have a load diagram, and by load diagram I just mean like this, just like, you know, the beam with the loads on it. That's what I would call the load diagram. If you take the load diagram and you integrate it, you get the shear diagram. And if you take the shear diagram and you integrate that, you get the moment diagram. Now, this note here on the bottom is pretty important. I mean, we're not going to be computing derivatives and integrals when we need to plot shear and moment diagrams. The relationship will serve as a great spot check when we do need to derive formulas. I think Friday we're going to start deriving formulas for shear and moment because this graphical approach will work like 99% of the time. There is one instance where it kind of doesn't work, or at least it doesn't work easily, and that's with triangular loads. And so on Friday we are going to have to derive an equation for shear and moment, because for triangular loads the area method really doesn't work, the graphical method really doesn't work. And so on Friday we're not only going to be deriving equations, but we're actually going to break out some Microsoft Excel. So on Friday just make sure that you have your spreadsheets and whatnot handy, because we're going to be doing some spreadsheet stuff in class, and then also your homework assignment for that weekend is to develop a spreadsheet. So just something to keep in mind. Now, like I said last time, what's important is, I would argue what's more important is to understand the relationships, the mathematical relationships between, you know, derivatives and integrals, because that's going to play into how we construct a shear diagram. So this slide here is basically my conclusions for the graphical approach that we're going to do. So the way this works is we have our load diagram, or the free body diagram of the structure that we're trying to draw a shear and moment diagram for. And so you start off with the shear diagram, and then you draw the moment diagram. So first off, let's talk about the relationship between load and shear. Okay, so at a given point, what we know is that the slope of the shear diagram is equal to the load. So, for instance, if you look at the beam that we're going to do, in between our concentrated loads, there is zero force. Okay, so if there is zero load, then in those regions, the slope of the shear diagram should be zero. Okay, and so that'll play into how we construct the shear diagram. And then between 2 points, the change in shear is equal to the magnitude of load. between those 2 points. So, you can see sort of at a given point and then between points. Now, between shear and moment, sort of the same idea. The slope of the moment diagram is equal to the shear. The change in moment is equal to the area of the shear diagram between these 2 points. Now, I want to be clear, our derivation was initially focused on just like distributed loads, but you can make similar conclusions about concentrated loads and moments and whatnot. In fact, your textbook, like the derivation I did for you in class on Friday, was just focused on like a variable distributed load. But the textbook says, okay, let's go ahead and do it for concentrated loads. Let's do it for concentrated moments. And you see that everything that we're talking about works. What we're going to do in here is we're going to sort of treat this like we did reactions. We're going to start with what I would call simple problems, and then they're going to get progressively more and more complicated. So we're going to start with concentrated loads. I think whenever I teach shear and moment diagrams, I always like to start with just concentrated loads because the geometry is easy, the math is easy, it's easy to see and easy to visualize. In fact, I'm sort of like changing up how I do this when I teach this topic, because usually what I would do is I would introduce a topic and then let's just do a bunch of examples. Today this semester I'm trying to focus my examples on making particular points. So today we're going to start with just making sure that we understand concentrated loads. So we're going to begin cultivating this graphical approach by first looking at this. So whenever you look at a beam, let's say we have a beam and it's subjected only to concentrated loads, because that's all we're going to deal with today. So just point loads. Between any of those loads, or between any of those point loads, there is zero force applied. So the load is zero between those point loads. So in those regions, if you have zero load, go back to those integral relations. What is the integral of zero? It is a constant, right? So zero load means a constant shear. What is the integral of a constant? It's a line. So zero load means constant shear, which means linear moment diagram. Okay, so you can make some conclusions about this. So for instance, I know the text here is kind of tiny, but fortunately you all can download this PDF and zoom it to your heart's content. So let's say you have a region in a beam that has a point load. What that point load is going to do is it's going to cause a jump in the shear diagram. You're going to have, a shear diagram here and then a jump, and then you're going to go to another shear. And the amount of that jump is going to equal whatever load you're talking about here. Now, if you look at the shear diagram, if there's no other loads applied, then think, what's the shear between, here, let me do my pencil. What is the shear in this region? Well, there's zero load, so the shear is constant. So, you're graphing a constant line. Now, that line has a slope of zero. Okay, well, integrate that. What is the integral of a constant? It is a line. Okay, so a constant shear linear moment. And then the slope of the moment diagram is equal to the value of the shear diagram. And so that's going to make our lives a lot easier when constructing these. When you have this sudden jump in shear, what does this sudden jump in shear do? It causes a sudden jump in slope. Now notice what happened to the moment diagram. We went from a high slope to a low slope. Like, remember how when you plot lines, like a high slope, you're going uphill really quickly, whereas for low slope, it's kind of flat. Both of those slopes, however, are still positive, right? Because the shear is positive. The shear, we have a positive value. As soon as the shear becomes negative, the lines, instead of going up like this, they go down like that. And so that's going to be really critical to understand as we begin this process. Any questions about the concepts before we jump into our first example, really exercise stuff? Like I said, we might actually have a somewhat short lecture today because I want to take this one step at a time. All right, let's jump into it. Okay, so first off, you should recognize this example. We've actually looked at this example a few times. This was our very first reactions problem. So you can go back into your notes and see how did we get that the AY reaction was 35.8 and how did we get that the BY reaction was 32.2. So that you can look that up. That's pretty easily. That's pretty easy to do. And even if you don't have your notes, I mean, you know, just some moments a day. We have 20 times 6, 30 times 9, 18 times, 30 times 15, 18 times 22, sorry, has got to equal some by times 30, and, you know, solve that out, and you'll get by is 32.2, and then sum your forces in the y direction to get ay is 35.8. That's pretty easy. Okay. So what I want to do is I want to take this beam and I want to draw the shear and moment diagram using the graphical approach that we're beginning to develop. But I want to look at this blue box. Okay. After we've finished the example, can we use the shear and moment diagrams to determine the internal shear and moment at a point 12 foot to the right of A? Okay. And what I mean by that is this. Let me stop the share. Okay, so this is the example that we were doing in class on Friday, okay? And if you remember, it was this very same problem, okay? And we broke out our secret weapon of structural engineering, the samurai sword or the lightsaber. We cut a section at x equals 12 feet, and we looked to the left, and we determined what was our internal shear and moment. And I want to make sure that everybody remembers the numbers that we found. We found that the V was 15.8 kips, and the moment was 309.6 foot kips. Okay, those numbers are going to show up again, but they're going to show up in a couple of different contexts. So just make sure that you have those sort of in the back of your head. Okay, everybody good? And again, you know, y'all know me. If you got any questions, please, you know, just shout them out. All right, I'm going to share the whiteboard or the notebook. Okay. All right. Here's the beam. Let me go ahead and make this full screen. Give me a sec. Got to get my cables and whatnot arranged. There we go. Okay. All right, so here's our, and we're going to draw the shear and moment diagram for this beam. Now, one of the things I'll tell you right off the bat is that whenever you're drawing shear and moment diagrams, it is a good idea to have a straight edge with you. So, you know, an old credit card or you know, a discount from a Kroger or something, a ruler, a scale, something to draw a straight line. Now, if you want to get really fancy, and you don't have to do this, this is by no way, shape, or form a requirement. But one of the things you could also purchase, like I said, if you wanted to get real fancy, is to purchase one of these. This is what's called a French curve. I don't actually, let me see if I can do this. This is a drafting tool. And the reason why they're kind of, I know they look a little wild, but they're kind of slick when you're drawing moment diagrams, because depending upon how you turn it, you know, we're going to have moment diagrams that have curvature, and these things are designed to pretty much fit any curve that you would see in a drafting situation. They're an old drafting tool. You can pick these up at like Office Depot or something, but that's what these are. Just thought I'd show you that. Right now, or today, we're not going to need it. Today, we're just going to do straight lines. Okay, so let me put this back. Okay, now whenever you're drawing a shear diagram, let's talk a little bit about format. I always find that it's a really good idea to draw down some sort of like faint dashed lines. Something kind of like that, to just give you some guidance as to making sure that you're drawing these things to scale. And there's no like hard and fast rule that you have to do this or that you must draw a certain number of them. I just do it just to make my work a bit neater. Okay. And then what you need to do is give you a place to start. So let's draw a horizontal line. Actually, let me do better than that. Let me scroll down a bit. let's do it like this. Okay, good. That's good for starters. Okay. Oh, I went past the line a little bit. I'm going to do this one more time. I'm a neat freak on this stuff. I apologize. Okay, I won't do it again, I promise. Okay, and so that's going to be my 0 line. The other thing that you do right off the bat, or there's two other things you do. The first thing is let's label this the shear diagram. So we usually put a little V next to that. We use V's for shears because it's like change in vertical. And plus, if we used S's, I don't know about you, but my S looks a lot like my 5s, and I'd have a hard time differentiating between the two. So we put V for shear, and then for the units, what we usually do is put them right here. Like we'll say that the units are in kips, so that every number that we draw on the shear diagram, we don't need to like keep writing kip over and over again. That's pretty common as well. All right, one final thing that we typically do. Shear diagrams, they tend to like go up and down and all over the place. And with some shear diagrams, it's actually kind of complicated to figure out, okay, what's my 0 line? Now, there's a couple of ways you could go about that. One way is you could use different color pencils, like use maybe like a black pencil or a black pen for the horizontal line, and then maybe use, I don't know, like a blue pen or a blue pencil to actually draw the shear diagram, so you would know, okay, that's the 0 line, and then everything else is the shear diagram. Another simple trick is to just put some like tick marks or maybe like some arrows on the shear diagram or on the 0 line, just so that you know, okay, that's 0. That's very common in structural analysis. And the reason why I draw it like that is because, when we're constructing shear diagrams for beams, we tend to draw them from left to right, and that's pretty easy. But with frames, you could have members going up and down and all over the place. And so by using arrows, it kind of indicates, okay, I'm drawing them this way. Okay. So that's just a convention that we might employ later on. Okay, let's start drawing the shear diagram. Now, whenever you're drawing a shear diagram, you start out on one side of the beam at 0, and when it's done and over with, if you start at 0, you better end at 0. Okay, and why is that? Because for the beam, the sum of forces in y direction are 0, and so all this is just a plot of the change in those forces along the beam. But when it's all said and done, you better start at 0 and end at 0. Okay, let me scroll up a little bit so I can see the beam. Okay. Now, whenever you're drawing a shear diagram, what you do is you basically just look at the beam and do what the beam tells you to do from a load standpoint. So I start at 0 and I look at A. Okay, what is the first thing that I see here? What's the first thing that I see? I see that. I see this 35.8 kips going upwards. So if I'm at 0, I jump up to right here. And what is that? 35.8. Now, and by the way, y'all get your keyboards ready because I'm going to be asking for help in the chat, or you can turn your microphones on, whichever works. But I'm going to be asking for help throughout all this. Okay, so I'm at 35.8, and then, okay, so I've jumped up, and now I keep on trucking. Let's put some letters on here. So this is A, this is B. Let's call this C, D, and E, just to put some letters on there so that we can have something to discuss. Okay, so our first load is at point, we're calling that point C. Okay, so let's talk about what happens from point A to point C. Well, I look on the beam between point A and point C, and I see nothing. There is nothing on the beam between point A and point C. Now, the shear diagram, whatever I draw on the shear diagram, has got to be, the slope of the shear diagram is equal to the magnitude of the load diagram. So I look between A and C, and I see nothing. Okay, so how do I draw a line with a slope of nothing? What does a line with a 0 slope look like? It's just flat, horizontal. So from A to C, horizontal. So this is 35.8 still. Now, what happens here? What do I see at point C? I see 20 kips. It says, yeah, if I'm Greg, so it's saying, Greg, go down 20. Okay, so if I'm at 35.8 and I go down 20, what does that put me at? I'm asking you. I want to make sure that you're with me on this. So if I'm at 35.8 and I go down 20, what's that put me at?
15.8.
15.8. There we go. Exactly right. And seconded. That's what I like to see. Good deal. Now, and then you keep on trucking. From C to D, nothing. A line with a nothing slope. Boom. 15.8. Now, what do we see here? I see it says, Greg, go down. And how much does it tell me to go down? It tells me to go down 30. Well, if I'm at 15.8 and I go down 30, what does that put me at? Negative 14.2. Exactly right. So now I'm dropping below. We'll put that there. Actually, I can write that a little small. Okay. All right. Same story. Keep on moving over. Now what do? I'm at negative 14.2. What do? I drop down to what? Negative 32.2. There you go. Move over to negative 32.2. And then what? Jump back up to 0. Exactly right. So whenever you drew your shear diagram, you always start and end at 0. And that was the case here. We started at 0, ended at 0. And so what that tells us is that the reactions that we came up with, they satisfy the equilibrium from a sum of forces in the y direction standpoint. Okay, so one of the things about a shear diagram, which is sometimes not understood when you're first learning about it, maybe if you learned about it in statics or deformables or something like that, but they actually serve as a check of your reactions. Because if your reactions were computed correctly, then you'll start and end at 0 in both cases. Okay, so that's something to keep in mind. Okay, now we've got the shear diagram done. Before I move on, I want to see if there's any questions about this. I don't want to rush this because what we're going to do is we're going to take this problem and we're going to add more stuff to it. Like, what if there are distributed loads? What if there are triangular loads? What if there are concentrated moments? What if there are hinges? Like, so I want to make sure that the fundamentals are solid, that the foundation is solid. To borrow from geotech, I want to make sure that we have a solid foundation before we build upon this. So everybody good on this? Okay. All right. Now, we've got our shear diagram drawn. Now we need to draw the moment diagram. Okay. Now, in order to draw the moment diagram, you go back to the slides, and what does the slide say? That the moment diagram is the integral of the shear diagram. Okay. Now, I don't know about you, but I would like to avoid doing a bunch of calculus. Like, if I can avoid it, I will. So let's go back to what is an integral? What does it mean to integrate a function? Remember, when you learn calculus, when you take calculus, calculus is designed, that whole field of study is designed to solve two problems. One, what is the slope of a curve at a given point? And to do that, we come up with the derivative. And then two, what is the area under a curve? And then to solve that problem, we come up with the integral, right? And then fundamental theorem of calculus says that derivatives and integrals are backwards of one another. That if you take the antiderivative, it's the same thing as the integral. So, okay. So I need to integrate this shear diagram, but they're just rectangles, right? It's not that complicated. So here's what I'm going to do. I'm going to separate this into like 4 rectangles. So this is 1, 2, 3, and 4. Okay. And so maybe I'll put these areas here. So let's take rectangle number 1. So rectangle number 1, we're going to say is, first off, I'm going to say that it's positive, and we're going to say it's 35.8 times 6. And why is it 6? Because it's 6 wide, right? So I'm just taking, this dimension times that dimension, just, length times height. So just to make sure everybody's awake, what's 35.8 times 6? There we go, 214.8. All right. Next one is positive, and we're going to say 15.8 times 9. All right, so somebody help me out. Somebody else. There we go. Positive 142.2. Now, the third one is going to be negative, okay, because it's below that line, right? This is positive, that's negative, and that's negative, okay? So just make sure that you get your signs correct. Okay, so this one's going to be negative, and this one's going to be negative. Now, instead of telling you the numbers, you tell me. So do the third one. Tell me what it is. I want y'all to be energetic and engaged on this. So 99.4, close this. 99.4 kips, and you get that by doing what? So B times H, which is, I know it's B times H. There we go. And this last one, what do we get? We got one more. There we go, 257.6. And we get that by saying 32.2 times 8. Now, I want you to. Yeah, and I have I put that there. But you're right. You're absolutely right. Now, I want to do a little check off to the side. Somebody in the chat do me a favor. If I add up all the positive areas, the two positive numbers, what do I get? Well, that's what you get when you add them all up. But when you add up 357 and then the area negative, you get negative 357. Now, that is actually a check of something, okay? What it's a check of is this. The shear diagram starting and ending at 0 verified that the sum of forces in the y direction equals 0. The check that the areas match one another is a verification that the sum of moments equals 0, okay? Because when we draw our moment diagram, we're going to start and end at 0, and we're going to start and end at 0 by using these numbers. Now, there's a reason why I'm doing it this way instead of just adding all, like Mr. Garrison was 100% correct. He just added up all the numbers and said it's 0, and he's right. There is a reason, however, I'm adding up the positive numbers and then the negative numbers, because there is one case where it will not add up to 0. And that's in the case of a concentrated moment, okay? And I've always found it's just a little easier, because sometimes with a concentrated moment, it's kind of hard to figure out, okay, do I draw it up or draw it down? And I've always found it's kind of easier to just calculate your positive and negative areas separately and sort of look at those. So But that doesn't really matter for now. What Mr. Garrison did was 100% correct for now. Okay, all right. So let's skip down a bit. Let's give myself a little bit more room. And I'm going to take these dotted lines. I'm going to sort of draw them down a bit further. All right. And then maybe one other thing I'll do is just make it a little easier for me for scrolling up and down in case I do that a bit, is let's write in, this is positive 214.8. This is positive 142.2, negative 99.4, negative 257.6. All right, let's do that. Just so that they're there on the shear diagram. And then maybe I'll shade this. By the way, you don't have to do the whole shading thing. You can if you want. Some people do, some people don't. For me, it depends on what mood I'm in. Okay, so that's our shear diagram. All right, let's draw the moment diagram. And I'm going to put the moment diagram a little bit lower. Actually, let me scroll down a bit. It's so much easier for me to draw a straight line when my hands aren't, dangling off the end of the screen. There we go. That's a lot better. So, moment diagram, foot kips. Okay, so let's draw this out. Now, again, with a moment diagram, we are going to start and end at 0. Okay, because hopefully if we've done this right, then not only sum of forces in the y direction equals 0, but sum of moments equals 0. We're probably on the right track since our areas worked out. Now, in order to draw the moment diagram, what we do is we look at the shear diagram. And we pay attention to our areas under the curve. Because remember, the integral of shear is moment. So by integral, we mean areas. So let's look at the areas under the curve. So we start out at 0, and let's look at this first region. Okay? Now this first region has an area of 214.8. Okay? So and it's positive. So that means I go up, and I go up to 214.8. How do I get there? Well, from A, because remember, I named this was like point A, this is point B, and then I called that C, D, and E. So from point A to point C, we have a constant shear. So the constant shear means a constant slope. Okay, and what curve in geometry has a constant slope? It is a line. Okay, so I draw a line from there to there, and that's my moment diagram. Now, let's pop quiz this. What is the slope of that line? Let's see if y'all are paying attention. What's the slope of this line? .8. That's exactly right. The slope of that line is the value of the shear diagram. So now let me think. Let's talk about that for a second. Okay, the slope is 35.8. That's a positive number, right? What does a line look like that has a positive slope? Right, it goes up like this. This is positive slope. This is negative slope, right? So the fact that the line is going upwards in that direction and that the slope is positive indicates we're doing something correct. So that's a check that what you're doing is accurate. Now, let's keep on trucking. So I'm at 214.8. What do I do from C to D? Well, how much does the area change from C to D? It goes up. How much does it go up? It goes up, what is that, 142.2? So if I'm at 214.8 and I go up to 142.2, what's that put me at right here? Making sure everybody's awake. So what is this point going to be? 352. It's not 352. You're close. Because 357. Yeah, it's 357. It's going to go up like that. So yeah, so this is 357. Okay. Now let's make sure that we're clear on this. Okay, what is the slope of that line? $15.8. So let's think about this from a geometry perspective. Okay, the slope of the line is 15.8. So does the graph make sense? Well, is the slope positive? Yeah, the slope is positive. It's going up and to the right. Does the graph make sense when you compare it to the previous region? Well, the previous region had a slope of 35.8, so they're both positive, but that one has a much higher slope than the one over here. Okay, so again, it's gut checks to make sure that what you're doing is right. Okay, what about the next region? Okay, now I'm at 357. Now I'm dropping down. Okay, so if I'm at 357 and I drop down 99.4, what does that put me at? What's 357? Sorry, minus 99.4, it's 257.6. So you can look into the crystal ball a bit and you can see, okay, this is 257.6. I'm at 257.6, and if I drop down another, what am I going to do from E to the very end at B? If I'm at 257.6 and I drop down 257.6, that's going to put me at the big old goose egg. So I am going to start and end at 0. Okay, which, oh, by the way, I forgot to draw my little tick marks. I need to do that here as well. And put my little tick marks on there. Okay, so I start and end at 0. All right. And so what does the slope look like, or what does the curve look like for these other two regions? Again, it's just a line. But look what's happening. It's down and down. Both of them are going downhill, okay, because they're negative. What's the slope of that line? Negative 14.2, exactly right, yeah. And then this slope is negative 32.2. Okay, that's exactly right. And so this right here, that's your moment diagram. We'll scroll up a second. Maybe like that. Okay. I want to give everybody a sec because I'm sure some of you are drawing stuff out. So I want to give you a sec, see if you've got any questions, if there's anything that anything we can clear up. I tried to understand this stuff for 2 semesters. Well, thank you. Hopefully, what we do here in a second is going to further enhance that clarification. Now, was there a hand? Mr. Atkins, yes, sir.
Sorry, I kind of skipped my. Now, on a homework assignment, if we are doing a homework here, all this stuff won't fit on one page, if I rough estimate here. So, how will you like us to do that? Way.
Well, you can scan multiple pages using Cam Scanner.
I know that, but I prefer to keep like one whole problem on one whole page. But
no, I understand. And let me go ahead and say this, okay? And this isn't to like scare you from what's coming down the line, but that's going to become a little difficult as we move forward. So here's an example. Okay, let's take deflections. Okay, so later on, what we're going to do is compute deflections, and in deflections land, you actually have to do this twice because you have to draw the moment diagram for what we call the real loads, and then another separate moment diagram for what we call the virtual loads. And then you have to like integrate it and those results together. So it's gonna become difficult in the future to do that. But let me be clear: as long as you're doing things neatly and it's easy to follow, you can. I don't have a problem if you use multiple pages, but you're probably gonna have to sooner rather than later. I apologize for that. Now, I want to show you something real quick, okay? And I'm going to stop the share a second because I want to go back to this, okay? Now, I want to make sure that what we just did relates to this right here, okay? So what we did here is determine the internal shears and moments at a point, at a single point. And what we found was V equals 15.8 and M equals 309.6. Now keep those numbers in your head, and I want to see if what we just did, if we can tie those two together, okay? And you're going to find this is pretty slick. Okay, so let's explore this a bit, okay? I'm going to scroll down a bit. All right. Now, let's determine the response at x equals 12 feet. Okay, so let me scroll up a bit, and I apologize for the scroll down. It's kind of hard to do that. Okay, now here's the beam. When we said x equals 12, we cut a section from the left supports. X equals 12 was something about right there, right? So this is x equals 12 feet. All right. So let's take each of these one at a time. Let's start with the shear diagram, okay? If I cut a section at that point on the shear diagram, where am I going to cut through? I'm going to cut through like right there. My question is, what is the value of the shear diagram right there? What is it? It's 15.8. That's what the shear diagram is. The shear diagram is telling you what is the internal shears at that point. And so at x equals 12, we get a shear value of a positive 15.8. That's exactly what we got here when we did all this internal shear and moment stuff. Okay? Now, what about the moment diagram? Well, what happens with the moment diagram? Okay? I'm probably going to get a spot like right there? Does everybody see that? I'm talking about this spot right there. So it's like, okay, I need to investigate that a little bit. Okay, let me zoom in on this portion of the moment diagram a bit. Okay, so determine the response at x equals 12 feet. Okay, so for shear, I'm just going to say by observation, the shear is 15.8 kips. What about the moment? Well, would you agree? How about this? Maybe I should try and redraw this part of the shear or the moment diagram a bit. So let me zoom into it a bit. So it kind of looks like this. It kind of goes up like this. And this top point is 357. This is 214.8. And we're trying to figure out like that point there. Okay. This dimension is 6 feet. And this dimension is 9 feet. Now, here's the thing. You can make this like some super complicated geometry problem, or you can go back to basics. Again, what is the slope of this line? The slope of that line is 15.8. Therefore, you want to know a simple way of determining what that value is? What is slope? It's just rise over run. So just take 214.8 plus the slope times the run. So the slope is 15.8. The run is 6 feet. What do you get when you plug and chug that? You get 309.6. So the moment is 309.6 foot kips. These microphones are expensive, so marker drop. Yes, sir, Mr. Adkins.
So I'm assuming there's going to be like a homework problem or exam problem where we have to first make the moment and shear diagrams, and then we have to determine what is the moment or shear at a certain point, correct?
That is possible, yes. That is possible. One other point I want to mention, remember that moment is just the integral of shear. So if you want to arrive, so I'll say another means. So here's like a zoomed in portion of your shear diagram, right? So you went up to 35.8 over, and then down to 15.8, and then over. If you say, no, I'm going to stop that right there and say that this is 12 feet, right? Let me ask you a question. How do I determine the area of that shaded region? I mean, let's just go back to geometry. I propose that's 35.8 times this dimension, which was 6 feet, plus 15.8 times 12 minus 6, or 6. What do you get when you check that area out? Spoiler alert, you get 309.6. So what I want to emphasize is that doing what we did on Friday serves as a spot check for what we're doing today. Like, let's look at this 309.6, right? Go back to your moment diagram, right? When you look at this moment diagram, almost like the individual value doesn't really matter, okay? What did we find? We found that that x equals 12 occurs in this region between C and D. Well, C, the moment is 214.8. D, the moment is 357. So I know that moment's got to be somewhere between 214.8 and 357. Now, when we did it by hand, we got 309.6. Without, going and doing the linear interpolation, we're probably doing something right, because it's got to be between 214.8 and 357, and we got 309.6. Okay, so again, just as a spot check to make sure that the graphical approach works, that's what's important. Okay, that's the valuable stuff. All right, now was that easier? Was that better than the past? Okay, good. Now, here's what we're going to do next time. So next time, we're going to take this problem and we're going to expand on it a little bit, because this is great and this graphical approach works wonders when only dealing with concentrated loads. Now, if that's all we could handle, I'd argue it's probably not super valuable, because as civil engineers, we're going to deal with much more than just concentrated force effects. We got to test it against distributed loads. So does this method work against distributed loads? And the answer is yes. The geometry doesn't get harder. It just, instead of computing areas of rectangles, we're computing areas of triangles. So we're going to take this problem and expand it and make it a little more difficult. But in the end, it's not difficult. It's just more. Okay. Now, for your homework assignment, I've got 2 problems for you. And I actually gave you the reaction values for one of them. So one of them, it's like, okay, let's just test it, make sure you can draw the shear and moment diagrams. And then the second one's a little more, okay, start to finish. It's like, I want you to go through that process once. I need you to do it like over and over again. And Wednesday, we'll do distributed loads. Friday, we're going to do Excel. So Excel, because for triangular loads, this kind of breaks down a little bit, but there's some pretty nifty stuff to do with triangular loads as well. That's all I got, everybody. I will see you all on Wednesday. Everybody stay safe, stay healthy, and we'll see you then. That's all I got.